Hello, everybody. Thank you for joining today's webinar. The title of today's webinar is Defining Product Shock Fragility. Just wanted to go over a few quick things with you. So we are using a new version of GoToWebinar software today. So there might be a few unexpected pauses. But please bear with us as we navigate the new software. A good webinar experience for all of you, but we also know that there might be a few a few unexpected pauses, so we'll try and work through those as quickly as we can. This is a Landsmont operation webinar, and Landsmont falls under the umbrella of the Physical Properties Testers Group, or PPT. And as you know, most of you would know by now that the PPT Group is a family of brands, all experts in the design and production of physical properties testing solutions. These solutions cover a range of physical properties, including tensile and compressed strength, torque testing, textile analysis, and real-world dynamics such as shock and vibration. The other companies in the PPT family are McMesson, Alluris, and James Hill. So if you are interested in learning more about the PPT group, I'm actually going to right now just put our PPT events page in the chat for you to take a look at if that is something that you want to do. That's also where you will be able to see all previous and upcoming webinars. So just for you to keep a record of. Just on today's call, you've got Eric Jonason, who is our presenter for today, and my name is Sharon, the organizers. And we have various support staff throughout the United States, Europe, and Asia. So please feel free to ask questions. You're able to into the question box throughout the duration of the webinar, and we will then try and address all of the questions that we have at the end of the webinar. If we find that we have too many, we will contact you directly to answer your question. The webinar is going to be recorded, and you will get a copy of the recording to the email that you registered with. If you want to review anything for additional clarity or have a colleague who is interested in attending but couldn't, please feel free to pass the recording on to them. But with that, I will pass it over to Eric, and that will be the start of our webinar.
Thank you, Sharon. And hello, everybody. I'm going to turn my camera on here at the beginning of the webinar just to introduce myself before I get going, and then I'm going to turn it off just to save some bandwidth so it doesn't cause any issues with the presentation. But I just wanted to introduce myself to those that you don't know me. My name is Eric Jonason. I am the Vice President of Technology for Landsmont Corporation. I have a longtime Landsmont employee, been with the company for over 34 years now, my only job since graduating from university. And I've been in a number of different roles with the company, from starting in customer support department, but also working in a laboratory, an actual test laboratory, Landsmont's own test laboratories, shock and vibration, for 11 of my career years, and spent the last decade plus being involved more in the measurement side of things, meaning field measurement or transport supply chain measurements, measuring shock and vibration, trying to make sense of that data, reporting on that data, characterizing, using that data to drive testing. So today, though, the last number of webinars that I've delivered have been focused more on the shock and vibration from the supply chain side of things. Today's a little bit different for anybody that's attended, including myself, that I'm going to actually talk about shock from a shock test perspective, a laboratory shock testing and performed on products. Why it's performed on products, meaning the actual bare products, unpackaged products, and as well as maybe some of the components that go into making products themselves. So should be interesting, I hope, again. And I'm going to go ahead and turn my camera off here and get going. And just want to say thank you for attending. So I've used this this slide. I'm going to revisit a couple slides, but that's because I think it ties it to the story here when I talk about, yes, packaging, transport package design fundamental, which I often use when I introduce a presentation that I'm performing, but that's because of the relationship here. Yeah, I'm going to talk about product testing here in a minute, but it fits into this equation, this basic fundamental that says a product's durability plus any required protective packaging have to work together to get things through an environment. And that could be a transport environment, supply chain environment. It could also be a product's, even at some levels, operational environment. So what's key to all these webinars that I'm delivering here as part of the 6-step method is that it's important to understand something about each one of these elements, about your product, how robust is your product, about your packaging, what do they contribute, and about the environment, because what do both of them have to survive or endure out in that environment. So it's important to know a little bit about all of those. In the past webinars, I've certainly covered the environment, the right-hand side of that formula, and now I'm kind of shifting gears to talk about the product side of it. I also, people have maybe seen this before. Another way of showing that relationship in a different way is saying that distribution environment, supply chain, transport environment has a whole bunch of bad stuff that can cause, not necessarily bad, but stuff that can cause potential damage to your product or your packaging or the product package integral solution. Shock, vibration, compression, temperature, humidity, atmospheric pressure, different things like that when combined together can pose potential risk of damage. And so what this basically says is, listen, if a product is super durable, if you look at the left-hand side of this chart, if the product is super durable, maybe you don't need packaging because it's so robust and durable. You don't need packaging from a protection standpoint, meaning from shock and vibration or the dynamics. You might need it for other reasons, cleanliness, theft, presentation, but you don't need it from a shock and vibration perspective. The other situations there from left to right, the second one, if my product isn't that durable, I need some protective packaging to get it through the supply chain. That's an okay solution. The third one over, if I don't have enough packaging, it's under packaged, you can expect to have damage. And the far right scenario, if you have too much packaging, you don't have damage, but you maybe have more cost than you needed in your packaging. And it's the last little icon there to the right is a sustainability icon that basically says it's an unsustainable situation if you are overpackaged. But back to the left-hand side of that, when we really focus on the product, so I put a line across the top there. Truly understanding what's going on in supply chain is key. How bad is it going to be? How high, or might my products be dropped within the supply chain, or what severity of shock might they occur in the supply chain? Because once I understand that information, I can use that to help me kind of assess what I learn in the product fragility testing. So, when you do product fragility testing, you're basically saying my product is this strong or that strong or robust. And, and eventually what you do is you use that information to compare against the supply chain, what you know about the supply chain. So it says, well, if I can drop my product without any packaging from 48 inches, and I prove that on a shock machine, but in the supply chain, I only expect it to ever be dropped no more than 24 inches or 1 meter, then again, you use that type of information to say, well, I guess I don't need protective packaging, cushion protective packaging from using both pieces of that information. So again, the relationship's important to understand. I'm going to speak a little bit more about specifically the product shock durability side of things. So I'm going to share a video here real quick. Why is product fragility important? Because bad things can happen. You can drop your products on the ground, and it can be kind of consumer electronics that you're familiar with, but what you're looking at here is not just some kind of cartoon. That's actually a protein. Okay, so that's a range from everyday what we all use is handheld devices that obviously have to be thought of in terms of their strength and fragility, but also things like even a molecule, right? How robust is that molecule? And quite frankly, if you noticed in that video, it is very fragile, or it is fragile. There are issues, and we know in that side of the biopharma side of things that things down to the molecular level are susceptible to shock and vibration. So it's important to understand, or be able to characterize what that really means can we define how fragile? And so when we talk about product fragility, we talk about it in terms of shock and vibration. And I'm going to just talk about shock today, but those are the two dynamics, that we take a look at and can characterize in a laboratory environment. And quite frankly, there is no, shock and vibration are really defined in terms of the same type of dynamic measurement, which is acceleration, some type of change in acceleration. Like in the field, we measure it with accelerometers. In the lab, we measure it with accelerometers, whether they're attached to a shock machine or whether they're attached to a vibration machine. So they're basically, the origin is the same. It's a change of acceleration. But what differentiates between, how do we differentiate between shock and vibration? So when we talk about shock, it's a non-periodic excitation of a mechanical system, and it's characterized by its suddenness and severity. So back to, thinking in terms of shock and or vibration. Shock is big. Shock is quick. It's much greater intensity than you would normally experience in vibration. So it's severe, and it happens quickly. They're transient events. They may or may not occur, and when they occur, it happens and it's over. Whereas vibration is thought of more as a continuous dynamic, where it's always there. If you're moving in a vehicle or on a conveyor, as long as you're moving, you are experiencing some type of excitation from vibration perspective. So shock is different. Shock is big, boom, and it's over. Vibration is kind of continuous motion and lower in amplitude. And shock, if we talk about damage associated with shock inputs, it typically causes significant displacements in the system, resulting in immediate damage or failure, thinking catastrophic failure. So it's not fatigue related. I take a big hit and I experience a big response, and that can be a catastrophic response. Something breaks versus something wearing over time. And we usually describe shock by shock pulses. And I'm going to show you a couple different ones here moving forward that you can generate from a shock test machine. But we describe shock in terms of shock pulse. A little bit more about shock pulses themselves before moving on to the machines. But shock pulses are described by the waveform, which is what I'm showing here. That signal that you see there is a waveform, an acceleration waveform measured by an accelerometer. The y-axis is in G's. That's acceleration in terms of G's. And the x-axis is time. So that's a waveform, an acceleration time history waveform. And so we describe the waveform in terms of its amplitude and G's of intensity, how many G's of severity or amplitude did it experience? And then we also describe it in terms of its duration. How long did it experience that change in acceleration? How long was that event? Was it a real sharp, quick event, or was it longer in duration, stretched out for some reason? And then we can also describe shock pulses in terms of their frequency. That shock pulse that you're seeing there is called, it's a half sine shock pulse. We say half sine. And what does that mean? That means really half of a sine wave. And we talk about vibration in terms of sine waves. And if you look, might be a little bit hard to see, but I drew a dashed line over that signal, and you can see, oh yeah, that's got the characteristics of a full waveform that I just overlaid on top of there. And knowing that, we can determine the frequency, the natural frequency of that shock pulse. The other really key piece here of information that you get out of a shock pulse is something that we call velocity change. And velocity change, for better or for worse, we describe that we use velocity change and delta V, which is also change in velocity, kind of interchangeably. And so I say delta V on the right-hand side there, or that's the little Greek symbol for delta velocity. You see those references quite often. And what does that mean? Well, it's really calculated. It's basically the first integration of one of these waveforms in the area underneath that shock pulse and above the zero line. If you integrate that, you get a real key piece of information from a shock analysis perspective, and that's that velocity change number that you see there. So not only do I have an amplitude of 30 Gs, which is good information, but it's not good information all by itself, but because we know it lasted over 26 milliseconds in this case, we or the computer, let's say, or the data acquisition systems do the integration on that and say, oh, that has 200 inches per second of velocity change. That's super important when trying to understand true severity of shock pulses, not just the acceleration amplitude, but also the velocity change associated with that shock event. And then lastly, real quick, the frequency, just like I mentioned, this is another example of a half-sine shock pulse. I know from looking at it what the duration of that shock pulse is. If I imagine that shock pulse, not as a half sine, but as a full period sine wave, I would say, oh, that shock pulse has a period of, which is t, of 20 milliseconds. And so a way of calculating the math-wise frequency or natural frequency of a signal is to say, well, natural frequency is equal to 1 divided by the period of the waveform. And so in doing that, for instance, in that case, I know, and the computer knows quickly to say, oh, that shock pulse, by the way, has a natural frequency of 50 hertz. And why is that important to know? Well, it's important to know when you start thinking, which is like the next webinar I would do, but in terms of vibration, that means any product component in a product that has a natural frequency of 50 hertz or close to 50 hertz, if it experienced that shock pulse, not only is the shock pulse, the amplitude of that shock pulse bad, but because it's kind of tuned to that same frequency, it would respond, greatly, probably in a very negative way, in a bad way. It would respond poorly, quite frankly, to that shock pulse, as opposed to something that might have a natural frequency of, say, 200 hertz or 500 hertz. So it's important to understand that because it also speaks a lot to the true severity of what's going on. So what does all this mean? In our history, in my company's history even, back in 1968, a gentleman named Dr. Robert Newton, Dr. Bob Newton at the Naval Postgraduate School, which is located out in Monterey, California, which is where Lansmont is headquartered, he developed something called the fragility assessment theory and test procedure, which was basically how can we characterize the fragility of products in terms of, what are the kind of key metrics and methodology to say this product has a fragility of whatever the values may be. And in our case, what we're going to talk about is, that you determine in this type of fragility assessment is what is its critical velocity change and what is its critical acceleration. Those are the two key figures there. This is an old paper. I'm not obviously trying to show too much detail there. I do have a copy of this old paper if anybody was ever interested in looking at that old information. But it was basically what's key here is that there is a minimum amount of both acceleration, G's, and velocity change, delta V, required before any damage to critical elements will occur. So what that says is acceleration, big G levels all by themselves, they might not look good or sound good, but all by themselves, just that number, 200 Gs, that sounds like a big number, and it is a big number. But if there isn't a lot of velocity change associated with that 200 Gs, you don't need to worry about it, believe it or not. And the opposite, or the alternate, is true as well. Velocity, you can have a shock event or a dynamic event with a whole bunch of velocity change, but if there wasn't a lot of acceleration along with it, who cares? Kind of, it's not necessarily a big deal. So both of those values are critical to understand when kind of characterizing fragility. I always try to think of ways of explaining, putting, and I don't know that this is simpler terms, but when you think of peak Gs, Gs, bam, the sharpness of a shock event. If you put a steel hammer hitting a steel beam, that is going to result in a very high G level. But it'll, even if you just ting it, any contact between those two surfaces will cause very high G levels. But if there's not a lot of velocity, really like swinging the hammer, then it's not such a big deal. And it's almost like if you think of electricity, it's very similar, voltage. So if even somebody gets hit by lightning, people can get hit by lightning and they can live through it. And why? Even though there might be millions of volts, because it happens so quickly, it still might hurt them. It will hurt them, but they can live through it because it wasn't experienced for a long time where it was allowed to, put some amperage into the person. So anyway, this whole process here that we're going to talk about with the machines allows you to determine both of those. What are the minimum levels of critical acceleration and critical velocity required before potential damage is going to occur to my product or the fragile element within my product? And then when we determine those values, what we do is we plot those. And when we plot those, which I'm going to show you here in a few seconds, that results in what we call a damage boundary curve, which looks like this. I'm not expecting you to look at all the detail there, but that is a damage boundary curve. That's an inset, that I borrowed from an ASTM test procedure, which I'm going to, or standard methodology, which I'm going to highlight here in a second as well. But that's what a damage boundary curve looks like. The other thing to understand about velocity change, how do I, people might say, what does that really mean when you talk about velocity change of an event? And what's important to understand is that it's directly proportional to free fall drop heights. Okay, so this is a table, and this shows the relationship. It's small letters here, but if you look at the top left, this says impact velocity equals the square root of 2gh, a very simple formula, but basically, as long as like if I drop anything in the real world on the ground or on the floor, and I know how high I dropped it, I can tell you how fast it's going when it hits the ground, the impact velocity. Why? Because G, which is acceleration due to gravity in that formula, is a fixed thing. It's a constant, right? Acceleration due to gravity, we know what that value is. So we can plug numbers in to that formula and say, well, if I drop something from 6 inches, it's going to have an impact velocity of 68 inches per second. If I drop something from 24 inches, it's going to have a velocity change or impact velocity of 136 inches. So understanding that kind of relationship or that formula helps me look at data like this, back to this shock pulse that I pointed out a few slides ago, 30 Gs, 26 milliseconds. That shock pulse had a velocity change of 200 inches per second. Well, if I look over on that chart, that's starting to approach the velocity change associated with a 48-inch free fall drop. And so when you look at these shock pulses, it doesn't necessarily mean something did fall, free fall was dropped, but the impact itself has an energy or severity associated with it, similar to if I was to drop that item from 4 feet or 48 inches. So it starts to give you, again, perspective on how serious or significant some of these events are. When you see numbers like velocity change, what does that number mean? You can look at these types of simple charts to give you a relative idea of severity. So switching over now, we went from Bob Newton's damage boundary paper in 1968 to this ASTM D3332, which is the standard test method for mechanical shock fragility of products using shock machines. It's basically the step-by-step methodology of how you go about using a shock machine to do damage boundary testing or fragility assessment. And I can't, obviously, these are copyrighted procedures. I'm just trying to show a couple examples, pages out of that overall procedure. And this procedure, I don't know the absolute year that it was established, but it was, I think, in the early 1980s. So it's, going on 40 years or so now that it's been in place, that basically walks you through how you go about doing this testing, with the end result being that you generate this damage boundary curve. And what we use in the lab, and finally get into some of the actual procedure, we use a shock machine for this, okay? So this is just an example of a shock machine that's used for damage boundary testing. This is a Lansmont shock test system. It's a big one. It's got 152 square centimeter table. We obviously make them in all shapes and sizes, from 15 square centimeters up to well over 200 square centimeters, depending on what types of products are being tested. But this is what one looks like. So it's that for that specific testing. So, and what we're really focused on when we do this type of testing is the surfaces that impact against each other, the characteristics of those surfaces. When you drop that table, what is the impacting surface? Because that determines what type of shock pulse that you get out of that. So we really focus our attention down in that area. And so if I zoom in here, you basically see the bottom, just focus on the blue right now, the bottom of our table. This is an aluminum table. When it hits these black, very hard, high diameter plastic pieces of material that's called Delrin, very stiff, very hard. When the table itself is dropped, impacts against those surfaces, that provides a very short duration, high acceleration shock pulse. When I say short duration, in the neighborhood of 2 milliseconds, 2/1000ths of a second, that's as long as that impact occurs. Super quick. So that results in when something is super quick or short duration, that means, back to when I talked about frequency earlier, it has a very high frequency characteristic associated with that shock pulse. So that's one of the ways that we drop this when we do damage boundary testing, is drop the table right onto these plastic programmers. The other way that we configure the machine to drop is to fill these programmers. We call these damage boundary programmers. We fill them. They can be filled with nitrogen. High pressure nitrogen, and there's a piston in each one of these, and that piston, when you fill them full of nitrogen, the piston pushes up to the top, and so now they're configured so that if I was to drop the machine, that these nose pieces contact, instead of the aluminum on the black, it's actually the nose piece on the edge of these plungers that contacts that piston, and that piston that's got pressure behind it. And so you can think of that as basically like a certain amount of cushioning that occurs in that configuration. So those are the two unique ways that we do that, the machine setup for doing damage boundary testing. And this is, I'm going to share real quick here, is what that looks like, just what the machine looks like itself. In this case, this is a machine that I work with here relatively close by to where I'm located. There's only 2 programmers. It's called the Model 95-115, but this is what it looks like. And I'm going to drop the table here in a minute in both of those different configurations so you can see what that looks like. First one will be and the arrow kind of shows you where the impact. occurs. Aluminum on Delrin. Here it's the plungers down in the piston. And you see the result there, the difference is you get the 2 millisecond half signs versus the long duration, what we call square waves. And I'll explain that here a little bit moving forward. Just switching back to my presentation here real quick. So, kind of show what was in that video, the differences. So just to show again the aluminum bottom of the table impacting against these Delrin programmers. This is just a felt material, a thin felt material that's used to in between the table and the Delrin, just to help eliminate some of the high frequency noise that would occur, the ringing that might occur if it wasn't there. But that's the two impacting surfaces that give you this short duration half sign shock pulse. And then this setup is basically trying to show you that the plunger with the nose piece on the bottom of it, that goes down inside the piston and hits the top of the piston. And then you get these what are called square wave or trapezoidal wave waveforms. Although both these scales are showing acceleration, or graphs show acceleration versus time, the scales are different here. This is a much higher peak G event. In this case, it looks like about 130 Gs, where this is only about 15 Gs, the one I'm showing here on the screen, and it's at a much longer duration. And so what I'm going to show you also is in the machine that I work with here, just as a way to demonstrate the effects of changing acceleration and changing velocity change, is we put together a modeled spring mass system. So that's what this is. This is a modeled product, simple spring mass system, a fixture that we can attach to the top of one of these shock machines. Okay, so what we have is a spring. We have a mass suspended to it, and that, in this case, that mass is a magnet. And then at the very bottom of that, I got a washer, a simple steel washer attached to that magnet. And what I'm going to do is I'm going to drop that, it's attached rigidly to the top of the table, but I'm going to drop that on my shock machine in a couple different ways, doing the short duration half signs, and then I'm going to do the long duration square waves and see how this spring mass model responds, and see if I can cause that washer to fall off of that magnet. And if I can, obviously, I want to know how much. How many G's did it take to do that, and how much velocity change did it take to cause that to happen? So the first type of testing that we would perform as part of this damage boundary testing or fragility testing is called step velocity testing. And we do that for establishing that value as part of this procedure. That's called the critical velocity change. So we use the short duration half sign pulses. We start the machine by raising it up very low to a very low drop height, which, again, remember, low drops, the height of dropping something is directly proportional to the delta V, or the velocity change, the speed at which it's basically hitting and or rebounding. And then so what we do is we start at a very low height, and then we slowly increment the height up, up, up until we get damage to whatever it is that we're testing, product, component, looking at the critical element. And what this tells us by doing this type of testing, it determines how high you can drop something before damage may occur. Again, it's telling you how high. It's not how many G's it can take from that height. It's basically saying, how high can I drop this thing all on its own before I would expect that damage would occur. And this goes back to that chart I had at the very beginning, product plus package equals environment, or has to equal to or greater than environment. If by doing the step velocity testing and establishing that critical velocity change, this allows us to tell us if at the end of it, are we going to need packaging even? Are we even going to need it? This, even before we go on to the next step, which is the critical acceleration side of the testing, this testing alone says, how high can I drop this? So when we do this incremental testing, it might be hard to see, but these are three shock pulses that are captured with our test partner data acquisition system. And it might be hard to see, but this is basically like 100 Gs on the first drop. This is about 120 Gs on this drop, and this might be 130 Gs. So I'm incrementing the machine higher and higher, and each time I do that, I get a little bit more energy, acceleration and delta V associated with these events. And what I'm really focused on as part of this testing is the delta V side of it. So now I'm going to switch back over to another video that focuses in on this spring mass model, so you can see what that looks like as I start this drop. So let me just load that real quick. Just kind of a quick shot to show big impact in the table on Delrin. But now what we do is we start at a low drop height, only a couple inches of machine drop height. Washer stays on. There's the shock pulse from that first drop. Now I raise the table a little bit higher. Washer still attached. I got my data. I go to the next drop, raise the table even higher. Small increments, but it's higher. And sure enough, the washer falls off. Very exciting stuff, I'm sure, for everybody. But that's basically what we're trying to determine through that type of testing is how, obviously cause that to happen, but then what are the metrics associated with what caused that to happen, the measurable, quantifiable metrics. And so when it actually falls off, what we do is we look at this shock pulse that we capture from the machine, and we say, again, I'm focused in this case because this is step velocity testing. What's the delta V? What's the velocity change associated with that shock pulse? And remember, that's equal to the area underneath of a shock pulse. And so that's what I'm really focused on here. And of course, again, computers, data acquisition systems automatically calculate all that. They do the integration and calculate that. So in this case, that becomes for that scenario with my spring mass system and that washer, that becomes my critical velocity change. I got half of what I'm looking for in my overall damage boundary testing. Okay, I got it. Now I'm going to switch things over and look at doing the step acceleration testing to determine the critical acceleration that basically says, okay, now I know how high I can drop that thing and before damage, how much velocity it takes at a minimum. Now I need to find out if I experience that type of velocity, how many G's will it take or be required to cause the washer to pop off of the magnet. So we switch the machine over to do this type testing. We switch it over to do those long duration square wave shock pulses. And what we do in this case is we use a fixed drop height. We don't increment the height of the table each time. We use a fixed drop height with a fixed delta V. And what that says is a fixed delta V of roughly 1 2/3 or greater than what the velocity change we established in the step velocity testing. So we want to go above and beyond that, and you'll see why when you look at the final damage boundary curve. But you want to go higher. You want to go, you'd think, oh, why would I want to go higher than that? That's just going to cause the magnet to come off, or the washer to come off the magnet. But it won't. Why? We could drop the machine from the full machine drop height, but if we limit the amount of acceleration that goes into it, even from that drop height, that magnet's not going to come off. So we want to go higher with this testing, or get higher velocity change. And then what we do, though, what we now control and vary is the amount of pressure we put in those damage boundary programmers that are underneath the table that have the pistons in them. And by varying the pressure, starting at a low pressure, nitrogen pressure, we control the amount of G's that get transmitted up through the table into the product, or in our case, that spring mass system. And so this is what those pulses would look like if I do 3 consecutive pulses, square waves. They look different, right? A little bit. I mean, they look similar in their shape kind of characteristics, but like this one's lower in intensity, this one gets higher, and this one gets higher yet. Not only that, but this one gets shorter compared to this one, and this one gets shorter yet. But remember, the area underneath these is equal to the velocity change. So if I looked at the value, which it's too hard for you all to see, but the value, the area here is basically equal to the area here, which is equal to the area here. And so the velocity change numbers for each one of these shock pulses is basically constant, close to constant. And the only thing we're varying is the amplitude. So we're slowly incrementing the G level we're exposing it to on each one of those drops. We're incrementally increasing that. And so I'm going to switch back over quickly to the video of what step acceleration looks like. Now we drop the table a lot higher than we do with step velocity side of things. If you think again, that's going to cause problems. If it doesn't, now I'm going to do the close-ups again. The camera was at the same position, so you can see the table going much higher in this case. Relatively low pressure in the piston. Washer stays on the magnet. There's the shock pulse associated with that. Here's the next one. Same drop height. More pressure in the piston. A little stiffer, but still magnet stays on, even with that shock pulse there. Now, even more pressure in the piston. Washer comes off. And I got my data associated with that. Switch back over real quick here. That's what the shock pulse looked like, again, when the washer popped off. And so what I take away from the data in this case is what's the G level? What was the G level when that occurred? I already, we're controlling the constant, the velocity change, or the area underneath that pulse. But what I'm really interested in this case is how many G's did it require? Like given a whole bunch of velocity change, remember that in the first step velocity testing, it only required like 60 some inches per second for the washer to fall off. Now with these big square waves, or the higher square waves, because I'm dropping it from a higher machine drop height, I'm giving it way more energy than what we determined in the critical velocity change. But because I was slowly incrementing this number up by changing the pressure, even though it's all that velocity change, washer stayed on until I reached some critical acceleration level. And so if I take the data now that I captured in both the critical velocity or the step velocity testing, and I plot those values, that's for the first round, those blue dots. I only showed 3, but here are 4 of them that I did from the short duration half science table against those Delrin plastics. The acceleration increases as well as the velocity change for each drop. So I plot those, and where failure or damage occurred, the washer pops off, I drop a line down through that point, and that becomes my critical velocity value on the damage boundary plot. If I do the same thing from the values I got on the critical acceleration, mine weren't super linear, but they are all meaning the same velocity change number. But really what I'm wanting to learn out of this is the y-axis, the height of those yellow lines where the washer finally falls off. And I did this quickly. You can get much tighter control on the repeatability of the velocity change, but it would basically remain constant in a tight range. And so during each drop, to the point where that washer falls off, that becomes my critical acceleration. Now I have 2 of the boundaries of the damage boundary. And what I'm able to do, there's always kind of a knee to a damage boundary curve, which takes a long time to describe, but there is always, a knee area to that shaded region. But what that says, when I say damage region, that means any combination of shock pulse that has, an acceleration level and velocity change associated with it in this region, you can expect that would cause damage to your product, to your component, to your fragile element. Anything outside of it, no problem. Doesn't even matter. I could see 200 Gs, quite frankly, in this case, or I could see 600 Gs. If it didn't have some minimum amount of velocity associated with it, that much, which was, again, like 65, 60, I forget exactly what the number was, but I could see 600 Gs if it doesn't have much velocity with it. So only when the two values of a shock pulse exceed those minimum thresholds would you ever expect to see damage. And so what this does by having a critical acceleration value, like in this case of whatever it was, 35 Gs, that's the takeaway from this testing that you would give to packaging designers, protective packaging designers, that says, hey, here's your target. Here's your target, packaging people. Design me something with a system, whether that's foam, springs, depends on the size and configuration of the product. But if I have a 35 G fragility with that product, your job is to design a protective system that will never allow 35 Gs into my product. So you go find the right packaging materials, the right suspension system to mitigate or attenuate any type of shock from getting into, at that amplitude, from getting into my product. And another thing that I wanted to share here quickly is, like, this is now what I'm showing. This is a screen capture of showing shock events that were recorded by one of our savers, shock and vibration environmental recorders, that is out in the supply chain. We can put those, attach them to crates, inside packages, send them out in the supply chain, get that data back. And this is a similar type of looking plot where I'm plotting acceleration versus delta V. Acceleration in the y-axis, delta V in the x-axis. It might look like a bunch of, again, most people might look at this when you get it back and say, I don't understand what I'm looking at. Well, think of it as almost like a way to assess, if you know damage boundary data, which I did from my spring mass system with the washer on it. If I sent that thing out into supply chain and it was exposed to all these events that the recorder recorded, would any of them pose potential damage to that widget? And what this basically says, if you think of it in terms of that damage boundary plot, there's a lot of stuff down in that lower left-hand corner or area, quadrant of that plot. But I really only see about 2, maybe 3 different events in the total that looks like had potential to cause damage for my spring mass model system. Again, this is real data, but this is a way of looking at that data to say, show me what I need to be concerned with. I know you collected a lot of stuff, but I want what in that data is significant. This is another set of data. The first one was something that was in a crate. This is one that was in a small parcel kind of package, an instrument that was in a small parcel package that went out in supply chain. So the data spread looks different. And you see, again, here are some events that have a lot of velocity change associated with them. And, 35, again, close to 40 Gs. So there's a number more, 1, 2, 5, 7, 8 events that are approaching damage potential in that situation for my fragile spring mass model system that I rigged up. But it's a way for me to look at a quick way at field data to say, based on what I know about my product, could I, are those events of concern to me? Is that what I'm seeing in my supply chain environment? Should I be concerned with that? So it's another effective way to use damage boundary results to look at other data. All right, going to wrap it up here pretty quick. What I just wanted to also mention is, kind of trends for us, just for people that might not understand a lot about who does shock testing. again, anybody with let's say products that are fragile, and that a lot of times you can think of consumer electronics, right? Basically, you think of the world today with mobile electronics, phones, uh, tablets, laptops, all the devices that we use that have to be super durable these days. So for Landsmont, our shock test systems, what we define performance in terms of what's the peak Gs that these systems can do, how many Gs can we generate? People always want more for various reasons. And how fast can they go? How much velocity change can we get out of those? Well, when I talk about velocity change, it basically means how high can I drop one of these machines? And in our standard, over my span at Landsmont, these 35 years almost, standard machine was like in this 288 inches, 300 inches per second. And that's based on, maybe let's say 4 feet of machine drop height. And that was a lot, for us, has been for a long time. You need to go above and beyond that. Every once in a while we stretch a machine, but you get a lot of energy out of one of these machines with that type of drop height. But over time, these machines, because of the change in products and in technology that's out there, we've been challenged by customers to make systems that can do more higher G levels, and do a heck of a lot more velocity change. So this is a shock machine. Looks a lot different than this one. There's a lot going on here technology-wise, but you can see these white bands. These are actually bungee cords. At some point, it's impractical to make these any taller, right? But if you want more and more velocity change, that's what you do. You build the thing out. Find a big open bay area and make your machine taller and taller and taller. And one of the ways we can add velocity change to our shock machines is to incorporate bungee cords. These are super durable, varying diameter. This is a pretty high diameter bungee cord. So basically, when the table is being lifted off of the base or from the ground or the impacting surface, these bungee cords are in tension. So it's like a slingshot. It's a way to get more velocity in a repeatable fashion out of it, as well as higher accelerations. So these can also get very tall, but with some of our machines, in various combinations, we can generate as much as 10,000 Gs. We can do impacts down to 1/10 of a millisecond, which might not sound impressive, but it's very, very, very short duration type of shock pulse. And we can achieve velocity changes upwards of 600 inches per second, approaching 700 inches per second. And we've progressed in that direction for quite some time because the robustness of products and components, as technology progresses, things are becoming more and more durable. So if you really want to kind of define the durability or the limits of those components and products, you need more and more performance from your shock machines. So, we do a lot of very high performance shock machines, and my last video is kind of show you what some of those just real quickly look like. But these are high performance systems, but it's not like they're for special people. These are for people that manufacture, again, the stuff probably many of you are looking at either on your mobile device or on your screens. Those people are using this type of high performance technology. Is showing different impacting surfaces, the felts. That example there, that was more than 2,500 Gs. So these are just some super high performance, high energy systems that are not uncommon for us. And you can think of a lot, again, the products that you all use, that I use, have been developed and verified, the reliability proven by testing that's been performed on that type of a test system. So with that, I'm going to say thank you. I hope it was informative. This is the type of topic that's almost better spoken about or taught over like a half day or a full day in-person session. It's a lot to absorb, no pun intended, by relatively quick webinar, but hopefully it gives you an idea of there's a method kind of to the madness of why people do this type of shock testing in defining one way or the other or characterizing their products. And so what I'm going to, next webinar on the 10th of October, instead of talking about shock, I'm going to talk about this kind of testing from a vibration perspective. So with that, thank you very much. I'm going to hand it back over or get Sharon back in the loop here and see if you guys have any questions we can answer. Thank you.
Thanks so much, Eric. So if anybody has any questions, you're welcome to pop it into the question box. But we do already have some questions, Eric, so I'm just going to read the first one out to you. So it says, in some pulses, there is a slight overshoot at the end of the pulse. I suppose there are physical limitations to how soon the acceleration can be brought to zero, but how significant or insignificant is this overshoot from a shock testing perspective?
Yeah, remember, I mean, so that can be, that was from the machine that I was using, and machines can be tuned very well. And the bigger the machines are, the harder it is, you can imagine, to make the shock pulses pretty and, clean, although we do a very good job with that, with adjusting the shock machines. But it is, the more programmers, the big damage boundary programs that you have under there, the levelness of those, the shimming, all of that comes into effect. And on some of the very high performance machines that I even showed there, if I was to show you the shock pulses, you would see next to nothing in terms of that kind of overshoot or undershoot. But remember also that if you see any of that, the amount of, I guess I would say, the energy that's associated with that typically is insignificant compared to the primary shock pulse itself. But that can be controlled. So good for someone pointing that out, and that can be controlled, and typically is on somebody that again, any of the folks out in Silicon Valley that are doing that type of testing, they have that dialed in pretty tightly. I can, again, always cautious to name companies, but you imagine every major company where you're putting their phone in your pocket has a reliability lab that's doing this around the clock and controlling those things very tightly. So hopefully that somewhat addressed the question, and feel free to reach out to me directly if you have more questions or concerns about that, but it can be
Thanks,
controlled.
Eric.
Mm-hmm.
Second question, when looking at environmental data, shouldn't you look at the vector sum of the three directions rather than each direction in isolation?
Yes. Yep. And you can do that. You absolutely do that. Our software reports on it that way. You can present it both ways, but certainly it's the vector sum. It also depends on how, when you do fragility assessment, you're usually doing that in controlled orientations. So it's important to look at all the above, I guess is what I would say. So if your fragile orientation on your product is base down or top down or left side down, then you're certainly going to focus on potential, if any of those types of events happen in that or towards that orientation. But you're right. You would look at the vector sum, and we report on the vector sum because all the instruments record triaxial data. So you get the triaxial resultant as a part of that vector sum.
Thanks. Next question. Regarding delta V, when using saver data to calculate the EFFDH, should you use the resultant delta V provided by the saver for the event, or should you square the delta V for each axis and add these squared values together to get the resultant squared velocity change for the event?
That's probably a long one to answer on the phone, although I would say we would, when I do this, we do the vector sum from the instrument itself. We use the vector sum it's, which means that it's critically important that when you're analyzing those events, that you're analyzing the primary event, impact, pulse. And it's also important, if you're looking to do equivalent free fall drop height studies from the field, that you first we call like calibrating whatever the system is that you're going to send out into the field to do the data collection itself. We calibrate that in the lab by kind of putting it through a series of dynamic events, drops or shock inputs, so that we can measure the response of that system so we know what we're putting into it, controlled inputs, drops, shock pulses. We measure the response of the decoy or the instrumented item, and then we send that out into the field. We get obviously responses from the field. We can then kind of back calculate, so to speak, as to what those events had the equivalent comparable energy associated with those, how to compare those things. Doesn't mean, when we do that too, we call that equivalent free fall drop calculations. That does not mean anything itself was dropped. That just means that it has the energy equivalent of as if you were to have dropped that item from 24 inches. I don't know if that makes sense or not, but we don't necessarily know what caused the big impact in the field. All we know is if I was to try to replicate that in the laboratory, the equivalent amount of energy, I'd have to drop that from something like 2 feet or 1 meter or something like that.
Awesome. Thank you very much, Eric. That's great. And again, thank you for joining us today. We hope you found it very informative, and please do remember that the next installment in the webinar series, which is defining product vibration fragility, takes place on October 10th, and you are welcome to register for that. Also, you will be receiving a recording hopefully tomorrow, but by the latest on Monday. And in there, we should include a link for you to register for the next webinar if you have not done so already. But I think that's all from us. Thank you very much. And
thank you.
We're going to end the webinar now. Hope to see
you
again
everybody.
at the
Thank you,
next
Sharon.
one. Thank